Good afternoon, everyone. Today we are going to see about optimal power flow. Optimal power flow. So the optimal power flow has a long history of development. It was first discussed by Carpentier in the year 1962 and took a long time to become a successful algorithm that could apply in use. So after starting this because here the constraints are very more, so it is the problem is very complex. The constraints are more, so the problem becomes very complex to solve. So it took so many years to develop a algorithm for this optimal power flow. So generally, you're sending a power. There are two buses are there. You're sending us this is the sending end example. This is the receiving end. We are sending a power of 11 kilovolt. 11 kilovolt. Say for example, 11 kilovolt. That 11 kilovolt is traveled to a very some long distance, like 20 kilometers, 30 kilometers. It is passing, and it is passing over not only to the one bus, it is passing over the many bus, because like if you take some areas, you can't able to tell like this is the only way to reach the particular place. Similarly, the power also will always flows to the optimal path. Optimal path, that is the shortest distance it will travel. So even though the distance between that two sending end and receiving end voltage is very long, it will always passes through the optimal path, and it will reaches to the particular point. Optimally it will reaches to that particular point optimally. So here that the power has to choose the optimal path. There are many buses in between, there are many feeders in between, but this power has to test the optimal path, so that the power also we are receiving, and the losses also will be reducing. So this optimal power flow is similar to the economic load dispatch problem. The only thing is that in economic load dispatch problem, how we solved is we solved using only one constraint or two constraint, and that is power balance constraint and as well as the minimum and maximum operating limits. But in the optimal power flow, there are many constraints, not only one constraints are there, like power constraints, reactive power constraints, real power constraints, then voltage constraints is there, then reactive power constraints, MVA constraints is there. Like that, many constraints are incorporated, so that the problem is very complex to solve. It is not that much easy. You can't solve a optimal power flow problem like normal three bus system like that. Even though you can solve, you have to make certain assumptions, like you have to make only two limitations, that is constraints you have to take, and rest all others you have to assume that as zero, or it is ideal condition. Like that only you can solve, but normally you can't solve a simple optimal power flow problem. Like if you see the definition of optimal power flow problem, this optimal power flow, it is common to express the optimal power flow as minimization of electrical loss. It is common to express the optimal power flow as minimization of electrical loss in transmission system, or to express as it is minimum shift of generation and other controls from an optimum operating point. Okay, so this is the definition of optimal power flow. Like you can also frame your own definition, but this is a common followed definition. Like optimal power flow as the minimization of electrical losses. So electrical losses is minimum in the transmission line, or to express it, minimum shifting generation. Okay, minimum shifting generation, so that other controls from the optimal okay, and other controls from the optimal operating point. So there is no any shift in generation. Okay, so there is no any requirement so that suddenly you can increase the generation. So there is no shift in generation. Okay, that is minimum shift in generation, and also other controls from the optimal optimum operating point. We could even allow the adjustment of load in order to determine the minimum load shedding schedule under the emergency conditions. So under the emergency condition, so we could allow adjustment to the loads in order to determine the minimum load shedding schedule. Okay, so load setting schedule is to be like very minimum, so that we can adjustment of the loads also will be very minimum. Okay, if the adjustment of the load is minimum, then the job done to the particular thing is also will be reducing. So maximum okay, like operating limits, it should be satisfied. So no, we much, so everything will be in the constant regardless of the objective function. However, OPF must solved so that the entire set of power constraints are present and satisfied at the solution. So entire many sets of optimal power flow objective function or constraints is to be added, so that to satisfy the solution. So we can't able to solve simply like the problem what we solved in our class. So like a special programming skills are required, special programming is required to solve this problem, that too with some minimum constraints. If the constraints are increasing, then the complexity of the solving the problem also will be increasing. Next, why we set up the generation dispatch calculation as an OPF. Okay, if entire set of power flow equations are solved simultaneously with the generation cost minimization, the representation of incremental cost is exact. Okay, incremental cost is exact. Further, the objective function that minimize the loss themselves, the power flow equations are quite necessary. So what it is said, the entire set of power flow equations are solved simultaneously. Like if you say take the one set of power flow equation, it will be like different objective function and different constraints. If you incorporate all other paths, it must be traveled. Na? So it involves many objective function and as well as many constraints. Okay, so our ultimate objective is to minimize the generation cost. Okay, generation cost and also losses, transmission losses we have to minimize. So the representation of incremental cost also should be exact. Further, the objective function that minimize the losses. Okay, so everywhere if you take the power flow problem, even most of the power system problem, if you take defaultly you can write minimize the total losses, like transmission losses. Defaultly you can like write. Why? Because this loss, minimizing the total loss is very important in every power system problem. Any power system problem if you take, you can easily write a word like minimize the total losses, transmission losses, generation losses, like anything you can write, because it must it handles almost all the problems what is solving. So minimizing the losses is very, very important thing. And with the power flow equations are taken into the account. So second thing is that the economic load dispatch solution, observe that generation limit only. Okay, if you take the economic load dispatch solution, only the generation limit only is there, like minimum and maximum operating limits. That is, it should not exceed minimum operating limits, and as well as it should not exceed maximum operating limit. That is there if you take any like economic load dispatch problem. With the power flow constraints, okay, many more power flow system limits are also included. Many more power system limitations, that is constraints, also included. That include the generated reactive power limits. Generated reactive power limits, that is Qi minus less than or equal to Qi less than or equal to Qi plus. This is also there. Real power limits also there. That is Pi minus less than or equal to Pi less than or equal to Pi plus. So reactive power limits also now added. And also limits on voltage magnitude at the generation and load buses. Like limits on voltage magnitude at generation and the load buses, that is Ei minus, okay, Ei minus less than or equal to Ea less than or equal to Ei plus. So voltage magnitude also, okay, so we have taken as modulus so that the limit will be in the positive. Okay, so whatever the even the minus symbol is there, it will make, if you put modulus, it will make that to plus. So that limit also there. And flows of transmission lines or transformer expressed in either megawatt or MVA. So MVA limits also there. Reactive power limits, MVA limits also there. So MVA minus Ij less than or equal to MVA Ij less than or equal to MVA Ij plus. So this set of operating constraint not allows the user to guarantee the generation dispatch of a generation, does not in fact force the transmission system into violating a limit, which might put into the danger of being damaged. So this many limits are there. This many limit, even one limits itself, the while solving the problem in exam, one limit itself you can't able to solve clearly, like that limits, optimality limits also has to be satisfied. Many of us skipped that step, forgot that step. Imagine, like you are having 1 2 3 4 operating limits are there. This 4 operating limits satisfying the 4 operating limits excuse me, with the constraints is very, very difficult, very, very difficult. So next, if we compare that represents the operation of the system after contingency outages. Contingency outages means, contingency analysis means, so there are two lines. For example, 5 kilometers of line is there. So whether that 5 kilometers without any disturbance, whatever the amount, whatever the power that being transferred, that should reach the this particular receiving end voltage or not. So within that, any contingencies happen, any outages happen. So like that, we are going to analyze. Okay, so that contingency analysis also, outages also, we have to consider. Okay, so say for example, 2 kilometers after some nodes, okay, from that some other transmission, like some other poles, we are taking that line. Okay, so in that some okay, transfer limits are there, and also some due to some circuit break installation, and due to some fault, some outages are there. At the end of the 3rd kilometer, some outages are there. So that outages also have to be taken in the to the account while solving the optimal power flow. So whether the power flow is optimal or not. So that fault also will be taken into the account. So these security constraints allows the, so this contingency outages are called security constraints, allows the OPF to dispatch the system in defensive manner. So whether whether the line, the power that is being transferred, it is being reached or not, that is the defensive manner. Like 1 kilometer once we are checking. Okay, 1 kilometer once, so whatever the power wave that is being sent, that is reached in the first kilometer or not, second kilometer. So second kilometer any fault is there, so again that constraints also will be added into the account. Okay, so some corrective action has to be taken, some corrective action. So now due to the modern power system, automatically corrective actions are being happened. Like some fault is there na, automatically the relay gives a signal to the circuit breaker, and it will relay will isolate the fault, isolate the fault, circuit breaker will isolate the fault. And nowadays in the foreign countries and all, there is one robot. Okay, so robot alone is traveling line traveling robot. Okay, so that robot alone traveling from the receiving station or some substations. So robot traveling for another 3 kilometers, 4 kilometers. So wherever the fault, okay, fault occurs in that particular place, so that robot is traveling automatically. If any two wires got damaged, so automatically that robot is making a small building or making a small connection, so that the corrective action also will be happens in a minute, in some minutes, like 5 minutes or 2 minutes, 2 minutes, that fault can easily clear. So imagine like now in the manual system, some lineman has to come to that particular place, he has to identify the particular fault, and again he has to make a phone call to particular that particular office. They have to collect that okay, joining, or whether some line to ground fault, everything. So they have to go take with some wires, so they have to reach that particular place. Like from office to that particular fault, maybe 10 kilometers, they have to travel for half an hour or 1 hour. Then they have to climb to that particular poles, and they have to correct that particular transmission line. Imagine it will take more time, like 1 hour of time, 1.5 hour of time. By the time we will not able to receive the power. So in that scenario, this also corrective action also will be possible. So OPF now forces the system to operate so that the contingency happen, the resulting voltage and the flows would still be within the limit. Thus the constraints might be following included. Okay, so this constraints like voltage constraints. Voltage constraints EI minus less than or EI. So if you take the line NM, if you take the, I said na, 5 kilometer of line, N and M alone, some outages is there due to some fault. Okay, so within that limit, it is falling or not. That also, that voltage, how much voltage it is being reduced with the outage, like that also we are able to calculate it. Next is MVA limit. Next is MVA limit. MVA limit also, like within the like reactive power, okay, also will be changing or not. That also it should be within the limit where the line outage happens in that particular line. That is NM, that is line outage, which implies the post contingency voltage on the bus K or the post contingency flow in the line IJ. which exceeding the limit for the outage of the line N. Okay, so that's what I said, which implies the OPF that would prevent the post contingency. Okay, so even post contingency, even that fault may happens in the particular N and M line, so it is already forecasting. That particular algorithm is forecasting, like a line N and M, some fault might be occur in that particular N and M. So we are doing the post contingency analysis. Okay, post contingency analysis, that is flow on the line I and J, which exceeding the limit for the outage of the line N. Okay, this special type of OPF is known as security constrained optimal power flow, SCOPF, security constrained optimal power flow. Okay, so what we are doing is we are making the post contingency analysis, whether that particular outage may happen in the particular line NM. So before itself, even if it happens now, what might be the voltage, what might be the reactive power changes, like that we are predicting in the before itself. So this special type of OPF is called security constrained optimal power. Okay, security constrained optimal power flow. So similarly, in this dispatch calculation, the only adjustable variables are generator MW outputs themselves. In OPF, there are many more adjustable control variables also. Not only like a generator output, there are many more control variables also. So that is generator voltage. Generator voltage they have to maintain constant. Then LTC transformer tap position. Okay, LTC on-load tap changing transformer, load tap changing transformer position, that also will be in the account. Then phase shift transformer tap position, phase shifting transformer tap position in the substation. So that also we should be taken care of. Then switched capacitor settings, capacitor in substations for reactive power compensation, switched capacitor. Sometimes in the line itself, the transmission line itself, some capacitor banks are placed in between, so that to compensate the reactive power. So switched capacitor settings also, that also one of the variable we have to taken into the account. Next is reactive injection for static wear compensator. Reactive power injection for static wear compensator, already you studied. In that reactive injection, how the reactive power injection be, that of the control variables we have to taken into the account. Next is load shedding. Load shedding down. So that also one of the constraints. Next is these line flow limits. Okay. Line flow limits also we have to taken into the account. So this many constraints we have to taken into the account, and then we have to solve the problem, optimal power flow. So these are the some of the control variables. This also will be taken into account. I repeat once again, that is generator voltage limits, that is control variables. Then LTC transformer tap position, then phase shift transformer tap position, then a switched capacitor settings, reactive injection for static wear compensator, then load settings, then DC line flow. Thus, OPF gives the framework to many control variables adjusted in the effort to optimize the operation of the transmission system. The ability to use different objective function provides a very flexible analytical tool. Okay, so OPF has many applications that includes, the first application is calculation of optimum generation pattern as well as control variables to achieve the minimum cost of generation together with meeting the transmission system limitation. That is, first application is calculation of optimal generation pattern as well as control variables to achieve the minimum cost of the generation together with meeting the transmission system limitations. Next is using either the current state of the power system or short-term load forecast. Okay, so current state of the power system or short-term load forecast, that is OPF can also provide the preventive dispatch. Okay, corrective dispatch we have seen, preventive dispatch. So for preventing from the particular outages or particular contingency. So that is called preventive dispatch if the security constraint also incorporated. So next is in an emergency, that is when some component of the system is overloaded or a bus is experiencing voltage violation. Okay, so in emergency condition, some component of the system is overloaded, some particular line alone overloaded, and also bus is experiencing voltage violation. So in that scenario also OPF can provide corrective dispatch, which tells the operator of the system what adjustment to make to relieve the overload or voltage violation. Okay, so suddenly voltage violation happening or buses experiencing overload. In that scenario, we can't those who are operators working in the substation can't able to identify or tell whether because of which system this voltage is violating, like that. So if we program all the things like that, so easily you can find out due to this only the violation is happening. So we can go for corrective dispatch easily. So that also one of the advantages. Next is OPF can used periodically to find out the optimal setting for generation voltage, transformer taps, and switched capacitor or static wear compensators. Okay, so it is also used to find out the optimum settings for generator voltages, that you know. Then transformer tap settings. Okay, so that also one of the very important thing. Then switched capacitors. Okay, so this many settings like OPF can used periodically to find out the optimum settings. So which settings that transformer tap should be there. Okay, so transformer tap will be of 4 or 5 tappings. So based on that, which tappings you should adjust so that the power in the output might be optimum. Like that also OPF can predict. And also switched capacitor. So how many settings we have to on? Okay, how many capacitor banks we have to on? Like that exactly we can find out the exact thing. Okay, so that simply like that, some 10 capacitor banks we can on, 20 capacitor banks we can on. Like that, a static wear compensator also. How many switches in that static wear compensator we can on. Like that, it can predict and tell you, so that you can easily go and on. No need of calculating, sitting in the substations, and no need of calculation like that. So simply like that, with this one program you can easily find out. Next, OPF is used routinely used in planning studies to determine the maximum stress that planned transmission system can withstand. Okay, so first itself, what we are doing is we are planning, we are giving maximum stress on the transmission line, and we are going to find out due to the maximum stress what will happen in the system. Like that, we are already analyzing priorly. priorly we are analyzing instead of any faults happened at particular time. In that time the OPF will give the command what to be on and what to be on. Like that. Instead of that, we are going for future planning studies. Okay, so in that we are over stressing the particular transmission line, and we are giving maximum full fault voltage. Okay, full fault voltage we are giving to the particular line, and we are going to predict how the changes might be. Like that, easily we can plan. For example, OPF can calculate maximum power that can be transferred from one area to another network to the another. Okay, so whatever the amount of maximum power that we can transfer in the particular line, okay, in the particular bus via the particular feeder, whatever the maximum power we can transfer, can easily transfer our power, no? So like suddenly some other feeders got damaged due to some fault, so we have to send the power via this transmission line only. But this transmission line already it can't able to withstand, because the conductor size and all, it can't able to withstand. But even then we are trying for another option. Some reserve line will be there. Okay, every system, if you take any city system, from load dispatch center to load centers and substations, like so definitely there might be one reserve. Okay, so even though it is traveling 30 kilometers or 40 kilometers, there will be some reserve transmission line will be there. Sudden fault happens in the particular line, some outages, anything happens in the line, so it will take many time, more time, like 1 hour time to clear that fault. By that time, what they will do is they will go for the another one option. So if you transfer like this, you can easily transfer this much power to that particular place. Like that, already we are going for like a future thing also. That planning also we are doing in the OPF. So OPF can calculate the maximum power that can safely transfer from one area of the network to the another network. Next is OPF can be used in economic analysis of power system by providing bus incremental cost. Okay, economic analysis, like what already we have done in economic load dispatch. So that analysis also possible. That is called BIC. So BICs are useful to determine the marginal cost of the power at the bus in the system. So marginal cost is winning cost. Like winning cost means, like next semester you are going to study. Like marginal cost means like two or as I said in the restructured power system, 2 or 3 generation companies are giving the bids, like I can able to produce the power for only 4 rupees. The first company is giving. Second company is giving, I can able to produce the power for 3 rupee 50 paise. Third company is giving, like I can able to produce the power for 3 rupees. So which power generally they will purchase in the market? Even though if you go for the market, the 3 members are telling 3 different rates, which from which like farmer you will buy that particular vegetable, means definitely those who are bidding with those who are giving with the least cost, 3 rupees, like 3 cost is there. So comparing to all others, 3 rupees is the very less cost for me. So definitely I will buy from those who are bidding 3 rupees only. So that is called the marginal cost of the power system. Okay, so that is the winning cost of that particular market. Okay, so that is called marginal cost. So when compared to, even though some other farmer can selling for 4 rupees, some other farmer for 10 rupees, some other farmer for 5 rupees. But who is winning the market? Only the person who is giving bidding with the least cost, that is 3 rupees only he is selling. So majority of the people, what they will do is they will go and buy from the 3 rupees person only. They will not going to buy from the 10 rupees person or 4 rupees person. First what they will do in the market, first they will go for all the they will walk, okay, from start to end they will walk. They will ask for the all the cost. Okay, so tomato means how much cost in this. So like that they may ask 10 members. So after asking 10 members, they may able to easily get the idea like which is the least cost. So the 3 rupees may be the least cost, means they will buy from the particular guy who is giving for the 3 rupees. That is least cost, that is the marginal cost or beginning cost of the particular market. So, to reduce, okay, even though they don't offer rupees profit, but they want to sell that product. Why? Because that market will run for only 3 hours, 4 hours, like that. So in case of power, even if you generate, you can't simply store that generated power. Okay, no equipment is there for storing the power. Can store only for very less amount. Very less amount. Even with that, you can light only LED lights, and you can light 1 or 2 lights or 1 fan like that for very few hours, 1 hour or 2 hours like that only. You can't able to store the power. Okay, so they also forced to reduce the cost to 3 rupees. So that is called the marginal cost of the power at bus system, at any bus in the system. Similarly, OPF can also use it to calculate incremental or marginal cost of the transmission power from one outside company through the system to another outside company. Okay, so similarly OPF can use it to calculate the incremental or marginal cost of the transmitting power from one company throughout the system to another outside company. Okay, so if they know one marginal cost of transmission power from the one company, so throughout the system to another outside company also, that might be very less only, very less. So OPF can reduce the transmitting power cost also. So that also possible in OPF. So this many advantages are there in applications are there in OPF.